In the last lecture, we discussed the various events which took place from the last glacial maximum around 20,000 years ago and today. We saw that there are a lot of abrupt climate changes from warm to cold and cold to warm, and our aim is to understand what caused these changes, because there is a possibility that as we change the world's climate, such abrupt changes may also occur in the future. And then we pointed out that since these changes are quite complex, we cannot understand what causes these changes based on observation alone, because observation of the past climate is based on proxy data, not real observation. You infer change in climate through tree rings or ice core or deposits in the bottom of the ocean. These proxy data are very valuable, but it is not possible to give a precise time at which this particular change occurred, because finding the exact time is very difficult with the past data, and so there could be errors of 100 to few hundred years. Therefore, it is important to combine the proxy data with climate models. Today we have very sophisticated climate models which take into account changes in the atmosphere and the ocean and land and biosphere. Although they are very good, they still do not resolve all scales of climate phenomena. A typical climate model today has a grid size of 50 kilometers of latitude and 50 kilometers of longitude. So, that means anything happening on a scale smaller than this is not really modeled from first principles. So, there are issues we have to worry about. And after we get these complex climate model results and compare with proxy data, if you want to understand how the changes occurred, we need simple models, because complex models are so complex that sometimes it is not easy to figure out why a certain change occurred. So, complex models are always looked at along with a simple model like the energy balance model we discussed earlier in this course. Okay. So, all the three have to be combined to understand what happened in the past. Now, one example I am going to give you is the well known work of Manabe, who got the Nobel Prize in 2021 in physics. So, he combined an atmospheric model with ocean model, and of course, atmosphere has equations for water vapor conservation, radiation heat transfer, and of course, the motions of the atmosphere in the zonal, meridional and vertical direction. Okay. And this is linked to the ocean. Ocean supplies moisture to the atmosphere through evaporation and also turbulent heat transfer called sensible heat flux. And the atmosphere provides the driving for the ocean through surface stress. That the winds in the atmosphere apply a stress on the ocean surface, which causes the ocean to move. Okay. And we saw that ocean circulation has two components, one driven by the winds, by the atmosphere, second due to changes in density caused by temperature and salinity changes. Okay. So, all these are incorporated in this complex climate model, which was pioneered by Manabe and his group at Princeton, and they were the first to look at what happens when the Greenland ice melts and provides fresh water to the Atlantic Ocean here, or there is a strong river discharge into the Gulf of Mexico here, which discharges a large amount of water. This water discharge either at A or at B will cause a change in salinity of the ocean. The figure on the right shows one of the examples of when the when the discharge was introduced at time t equals 0 here, the thermal Haldane circulation weakened for about 500 years and then it recovered. And the next graph shows how the sea surface temperature change in response to the melting of ice here, and the change of sea surface salinity because of fresh water addition, and how it changes the vertical motion in the ocean. Okay. Now, here is the time series of the thermo-Haldane circulation, that is the circulation in the meridional and in the upward direction, and the black line shows a simulation run with no disturbance. That simulation called the control, in which the carbon dioxide is maintained at pre-industrial value, and the next simulation is where both the amount of carbon dioxide and aerosols were changed as observed in the last 150 years. Okay. And you can see that on addition, on account of changes in carbon dioxide and aerosol, by around year 2000 this circulation begins to weaken. Okay. The circulation measured in Swed groups, which is 1 million meter cube per second. Okay. Now, this is a cause for concern, because according to this model that change occurs around the year 2000. Other models might give a change at a little later date. So, what this simulation showed more than 24 years ago, that increase in carbon dioxide can induce a change in the thermo-Haldane circulation around the year 2000. Okay. Now, this simulation was this work was published in year 2000. So, at that time they were not sure whether the circulation was actually changing. Today we know that the thermo-Haldane circulation has indeed weakened. Okay. But you notice that in the control simulation there is a fluctuation of the thermo-Haldane circulation between 19 and 16 Swed groups, which is a natural variation. So, year to year variations of this thermo-Haldane circulation is a part of natural climate variability. Only if the circulation goes below around 16 Swed groups that we should start asking whether it is due to increase in carbon dioxide. But this is a paper published 24 years ago. Lot more work has been done in the last 20 years, and we will discuss those now. Now, there is another work done around the same time by Joachim Marotzke, who took a very simple pure ocean model, no land, and he looked at how sensitive the circulation was to the temperature difference between the North Pole and the South Pole. Okay. In one simulation he had 0.6 degree difference, very small difference. In the other case he had 3 degrees, and you see that the circulation has changed substantially. So, the thermo-Haldane circulation is sensitive to the temperature difference between the Arctic and the Antarctic. Okay. So, and we know that due to global warming, this temperature gradient is going to change. Okay. So, this simulation showed that the changes in the temperature difference between the northern and the southern hemisphere causes a change in circulation. Okay. So, the shading here represents temperature higher than the minimum in the southern hemisphere. Okay. and that is larger here when the temperature difference is small than here when the difference was large. Okay? This is a thing we will look at a little later. So, here I mentioned many other simulations which occurred after the work of Manabe and others in year 2000, and so we will look at some of them. Now, there have been projects called Community Model Intercomparison Project, that is many groups of people now today run couple models. They get together and come up with a certain scenario, and all of them do the same simulation with the same scenario, and then they compare each other in order to understand how sensitive the Atlantic meridional ocean circulation is to the way that model is configured. Okay? Because there are still differences among models in terms of resolution, in terms of how clouds are represented. So, there are differences in the way they respond to AMOC. Okay? So, we will look at some of them. The one simulation I will talk a lot about in this course is the one done at the National Center for Atmospheric Research in Boulder, Colorado. They ran one simulation which was remarkable, called the TRACE 21K, Transient Climate Evolution over the last 21,000 years. Okay? From 21,000 years ago to 1990. Okay? It is a fully coupled ocean atmosphere model. This version is called CCSM3. Okay? The resolution is around 375 kilometers by 370 kilometers. There is little what you might call low resolution. That is because you are running the model for more than 20,000 years. So, you cannot afford to run a high resolution model. You can run a high resolution model for 100 years, that is possible today, but you want to run for 20,000 years, you have to compromise on the resolution. So, they decided to look at a fairly coarse resolution, but the ocean model has a higher resolution, because the ocean model has a high resolution because near the equator, to resolve the circulation we need high resolution. And then this model was forced with changes in the orbital motion of the earth. All of you know the earth goes around the sun in an elliptic orbit, and the earth's rotation axis is inclined by about 23.5 degrees, and where the earth is pointing called the precession, that also now is towards the pole star, but it has changed. So, when you run a model for 20,000 years, you have to account for the changes in these orbital motion of the earth, changes in greenhouse gases, changes in ice sheets, and changes in the amount of water which melts and goes into the ocean. So, all these are imposed. Now, of course, this is not perfect. Ideally, the model should generate this, but that is more complicated. But since we have a fairly good idea about how Earth's orbital motion changed over 20,000 years, and from ice cores we have a good idea about the greenhouse gases, how they change. We have some idea about ice sheets from proxy data, and we have some idea about the meltwater flux from the changes in sea level. Sea level changes can be monitored by geologists by looking at what is happening along the coastline of many countries, and so we have a fairly good idea if the sea level changed by a large amount over hundreds of years. Okay. Now, the advantage of running a climate model is, in addition to changing all these things, we can also change each one of them separately. They looked at how the circulation changed only we change orbit. The other simulation was keep orbit constant, ice constant, meltwater flux not there, but only greenhouse gas changed. Then they had a simulation where they kept orbit, greenhouse gas and meltwater flux unchanged, but ice sheets were changed. Finally, they changed only the meltwater flux. So, the beauty of these simulations which is done both together and individually is it helps us to identify which forcing is contributing to which change. Okay. This can only be done with models. In the real world, all these are changing together. Okay. Real world is complicated, but in the model world we have the liberty to hold one of the things constant, and that enables us to understand how much each of these things are contributing to changes in ocean circulation. So, when you start a climate model simulation, you need an initial condition. So, what these people did was they started from a previous simulation which had simulated the last glacial maximum. That is, you run a model for a long time, hundreds of years, giving the boundary condition of the last glacial maximum 20,000 years ago. If you run the model long enough, then the model reaches a quasi steady state, okay, which gives a rough idea of what was the circulation of the ocean at that time. And then you start the changes in solar radiation, greenhouse gases, ice sheets, coastlines will change, and so will the meltwater flux. Okay. And the meltwater flux was reduced in two scenarios, one around 14,200 years and the other around 14,670. So, this was to simulate the impact of meltwater fluxes. Okay. So, to assess the contributions of carbon dioxide and orbital forcing to the boiling Ellerod warming, which we saw was a major event, they performed two more experiments to understand this part. Okay. With and without changes in Atlantic meridional circulation. Okay. So, they have done various experiments, and we will discuss many of them in this and the subsequent lectures. So, just remind you, this is a global coupled ocean atmosphere sea ice land surface model with vegetation, and it does not have what is called flux adjustment. About 20-30 years ago, when they ran a coupled model, they found that the coupled model could not reach a steady state. The ocean temperature either was decreasing or increasing continuously, and this is unrealistic. So, they realized that there are some problem with the way model occurred. So, to ensure that the model reaches a quasi steady state, they occasionally adjusted the flux at the ocean atmosphere interface. This is of course not right, but 20 years ago they did not have a chance, but in this particular simulation done in around 2007, they had managed to improve the model so that they did not have to do flux adjustment. This is a big improvement, because you are not doing any fudging or adjusting the fluxes so that the ocean reaches steady state. Okay. And as pointed out, all versions were done it's a spectral model with T31, which is equivalent to 3.75 degree in latitude and longitude. Okay. So, the land has vegetation, plant type, soil, column and so on, and of course, glaciers, lakes, wetlands, urban areas are all specified. Okay. And the ocean model is called the parallel ocean model, and it has 3.6 degree resolution, but near the equator they have 0.9 degree. So, that they resolve the circulation close to the equator. Okay. So, there is also an ice thickness model, which is very important for the present discussion. Now, here is an example of what we know about the sea level rise in the last 20,000 years. Okay. The sea level was around 125 meters below the present, okay, and gradually started increasing as the world global temperature increased, a gradual increase till about 15,000 years ago, then it increased very rapidly for a few thousand years, then gradually, then another rapid increase, and then a gradual increase. Okay. This data is from two different sources, where sea level data is easy to infer from the past data of the seashores. Okay. And of course, there are some small differences between the two data sets, which is to be expected because this is a proxy data. There will be some variations. And the two rapid sea level rises are given the word meltwater pulse 1A or IA and meltwater pulse IB. So, this 1A and 1B you should remember because we are going to see the impact of them. So, again to remind you, in this simulation what is prescribed, the history of greenhouse gases changes is prescribed, not calculated, and we are going to discuss only the period 22,000 to 14,000, that is later on we will discuss the whole period, and then changes in insolation due to changes in Earth's orbit around the sun is also given from astronomy. Ice sheet locations are specified from past observations, and melt discharge, as I mentioned just now, also specified based on sea level rise. And of course, the differential equation governing the conservation of mass, momentum and energy were solved numerically on the Jaguar supercomputer at the Oak Ridge National Laboratory. What did this result show? Now, this figure shows on the top the changes in incoming solar radiation at 60 north, because this is what influences what happens in Greenland. Okay? And we will talk about it later in the next few lectures. So, the climate of the polar regions is influenced by not the global mean radiation of 1360 watts per meter square, which we discussed, but how much radiation is falling in the polar region. So, the characteristic latitude is 60 north here. Okay. So, you can see that in the period from 22,000 years ago to 10,000 years ago, the radiation increased from around 470 watts per meter squared to 520 watts per meter squared. By 100 watts per meter squared, it changed due to changes in the Earth orbit around the sun. And on account of that, the carbon dioxide increased from around 200 parts per million to around 260 parts per million. Okay. So, that increase you can realize is because as the ocean warmed, the carbon dioxide dissolved in the ocean came out. Okay. So, that was the main cause. Then this shows the sea level rise, okay, and the black is the observation here and red is the simulation. And you can see that the simulation is not bad, not perfect, that it shows the sea level rising from around 130 meters to around 100 meters about 14,000 years ago. Okay. The rest of the simulation I will discuss later. In the subsequent graphs here, it shows the North Atlantic deep water formation due to circulation changes in that region. And again, the black is observation and red is simulation. And you can see that the simulation correctly shows a slight decline in the Atlantic meridional ocean circulation. Then it begins to increase rapidly around 14,000 years ago. Okay. And to remind you, this is called the Heinrich event, and then finally we will talk about the Younger-Dryas and the Boiling-Euler events also. Okay. Now, the surface at temperature both in the Greenland and in Antarctica is shown here, And you can see that from around 20,000 years ago, when the simulation really started, to 14,000, the simulation reproduces, not perfectly, but more or less the rapid increase in the air temperature around the time of the boiling rod period. Okay. So, this will discuss in detail what caused that. Okay. And then we see that in the southern hemisphere, that is the Antarctic region, the changes are somewhat different. I want you to keep this in mind, we will discuss that later, that the large increase we saw during the boiling rod phase here of the order of, in Greenland, of the order of around 12 degrees is not seen in Antarctica. So, clearly the unusual event which occurred around Greenland around 14,000 years ago were a local climate change phenomena, not global, because we say Antarctic did not show the change. In addition, you see that when the temperature decreased in the period from around 18,000 to 16,000, this is so called the Heinrich event, which we will discuss, which happens because icebergs break up and fall into the ocean in the northern hemisphere. When that happened, the Antarctic region began to warm. So, you can see that the changes near the Arctic and Antarctic are occurring in the opposite direction. Okay. And this is called the seesaw, that is, the two hemispheres are not going together, but they are going in the opposite direction. So, this is a very important thing to understand, that the two hemispheres climate do not go together because of various reasons, both in terms of the amount of radiation coming from the sun is not the same in the two hemispheres, and the role that circulation plays in controlling the climate of the Arctic and Antarctic are quite different, because remember, Antarctic is a continent surrounded by ocean, which it has a circumpolar current blowing around it. Okay. It is sort of isolated. We talked about this when we talked about the ozone hole problem, that one of the reasons why ozone hole developed Antarctic is because it is isolated. Once the ozone was depleted, it was not easy for air from outside to come into Antarctica to reduce the depletion. Arctic is different. Arctic is an ocean surrounded by land. So, Arctic and Antarctic are very different. Antarctic is a land surrounded by ocean, Arctic is an ocean surrounded by land. So, that distinction alters the way it responds to large scale climate changes. So, these points we will discuss further. Now, let us look at the close up of what happened there. Okay. We are looking at now 20-year average temperature, okay, and the top is the Greenland ice core, bottom is the Antarctic ice core. And here first look at the red line, okay, which corresponds to the meltwater flux changes that were introduced in the model, the red and the blue. Okay. And so, what it shows is that the way you introduce a meltwater flux alters the way the warming occurs. Okay. So, in the blue one, a meltwater flux was introduced around this time, and that caused a temperature change, while in the red case it was not reduced here, but it reduced here. So, this clearly shows that temperature in Greenland is sensitive to when you introduce and where you introduce this fresh water. Okay. But it has no impact on the southern hemisphere. Look at Dome Sea, There is not much, there is small difference, but not too much between the red line and the blue line. Okay. Now, they also did experiments in which they changed carbon dioxide, but not the other parameters. And what you can see from this is that the carbon dioxide change, okay, and the change in the orbital, this one dotted one is the change in orbital parameters of the earth, and the green is the change in CO2. These do not contribute to the warming of Greenland. Okay. So, quite clearly this simulation shows very clearly, because they were able to do separate simulation in which they did only meltwater flux, only orbit and only CO2, and they are able to show that only the red line simulation, okay, was able to reproduce the observed increase, which is in black here, okay, and this was not seen in the southern hemisphere. So, we will have to look at it further. Okay. So, this paper they say they are able to simulate the abrupt recovery of the Atlantic meridional ocean circulation that triggers the transition from the Heinrich event, which occurred due to collapse of the ice sheets, to the Bolling-Aileroyd warming phase. Okay. And their introduction of meltwater flux was able to produce the warming in the Greenland region, and they also observed the model had an overshoot, okay, and this occurred mostly in the northern hemisphere. They were also able to show that in addition to meltwater flux, the increase in carbon dioxide of 40 parts per million also was important for the Bolling-Aileroyd phase. So, what we conclude from their work is the sudden warming that was observed for a very short period compared to the total period of 20,000 years was due to the introduction of freshwater fluxes by the melting of the ice, as well as the increase in carbon dioxide. Okay. So, and this can be brought out by looking at the model simulation, looking at the two broad changes that the model shows. One is warming over most of the globe with higher warming in the northern hemisphere, and another mode where there is warming around Greenland region, but cooling everywhere. Okay. This mode is called the global mode because it warms most of the world, and this is on account of the change in carbon dioxide. Remember, carbon dioxide is fairly well mixed in the atmosphere. So, once carbon dioxide increases and traps Earth's emission, it will have an impact globally. Okay. On the other hand, the introduction of fresh water near Greenland on account of melting of ice in North America and Greenland is a local phenomena, causes local warming because of the changes in the Atlantic meridional circulation, and the changes in Greenland and Antarctica are opposite. This is the seesaw, bipolar seesaw mode. So, the model was able to correctly get both these and was able to explain which forcing contributed to which mode. So, the global mode is contributed by greenhouse gases, and the bipolar mode is contributed by the freshwater introduction to the ocean near Greenland. And that is also seen when you look at the cross section of the ocean near Greenland. Okay. In the glacial mode, you can see that the surface salinity was low compared to the salinity in the deep ocean in the Atlantic Ocean, and once they come to the Heinrich phase, where a lot of ice fell into the Greenland region, it changed the salinity at the top level, okay, because of change in circulation, and during the boiling Elrod phase, that change was altered because of the warming of the region of Greenland. So, they were able to show not only what happened at the surface or what has happened deep in the ocean. As a matter of fact, you must remember that the proxy evidence cannot give you this kind of detail. You cannot from proxies get information at each level of the ocean, not possible. Okay. So, we will continue the discussion in the next lecture, because there is a lot more to point out how these changes occur. Thank you.